says Chapter 11, Example Problems, and this is the last chapter of General Chemistry 1. There's about 11 or 12 examples, and we may need to break this up into two parts, but let's just see how long it takes. We'll jump right in with example 11.1. It reads, determine how much faster a helium atom moves on average than a carbon dioxide molecule at the same temperature. We're going to use a root mean squared formula for speed, which looks at a ratio of their root mean squares as well as their molar masses. Now this is comparing one compound to another, or an atom to atom or atom to molecule or molecule to molecule. It doesn't matter which way the ratio or which atom you set to be 1 and 2 in the formula. However, as it reads here, there's a good rule of thumb just so you keep everything consistent. It says when solving a problem such as this, it is generally best to label the one that you know is the lighter of the two molecules as molecule 1 and the heavier as molecule 2. The reason why is when you work out the math of it, it will give a result that's greater than 1, and that's a little bit easier to interpret and wrap our mind around. So using this formula, let's take a look at how we can do this. So we'll have the molar mass of helium, which we get directly from the periodic table, and that is 4.003 grams per mole. Carbon dioxide, of course, we need to add up carbon and 2 oxygens, and we've done that before, and it's 44.02 grams per mole. So what we're going to do next is just look at the ratios. So we'll look at the ratios of the carbon dioxide to the helium, and notice the heavier is on top, the lighter is on the bottom. We take the square root of that and we get a value of 3.316. So very simple. You just take the ratio of their molecular weight or atomic weight, take the square root, and then you get a value. The value, if you set it up with the heavier on top, it should be greater than 1. What this means is that the helium atom moves 3.316 times as fast as carbon dioxide molecules if they're at the same temperature. So if we have the same conditions, same environmental conditions, and specifically like temperature, pressure, and so forth, the speed, or how fast they're moving, velocity and such, will be dependent upon how much mass is in it. Thing to remember is that the relationship between molar mass and molecular speed is reciprocal. And that means that a carbon dioxide molecule has approximately 10 times the mass of a helium atom. Therefore, we should expect the helium atom on average to be moving approximately whatever the mass ratio is, the square root of that. And it's 3 times as fast. So not bad. Let's take a look at the second example. Calculate the pressure exerted by a column of mercury 70 centimeters high. Express the pressure in pascals, in atmospheres, and in bars. And here's a equality that we'll get, that the density of mercury is 13.5951 grams per cubic centimeter. We're going to use a formula for pressure which relates height of a column, density of our material, and the mass to calculate our pressure. It's important that the units all work together so that they cancel out and you can actually get the pressure units that you're looking for. So that means that the height must be expressed in meters and the density must be expressed in kilograms per cubic meter. We can't leave it in centimeters or we're not going to get our pressure unit. Pressure unit coming from physics, most of these are derived in kilograms, meters, seconds. Excuse me. So for the height, we can put that into meters just converting from centimeters, knowing that there's 100 centimeters in 1 meter, we get 0.700 meters. We can also take our density, which is given in grams per cubic centimeter, and we can put that in kilograms per cubic meter. So first thing that we can easily do is to convert grams to kilograms. There's 1,000 grams in 1 kilogram. The next thing we can do is to convert cubic centimeters to cubic meters. You should remember from the beginning of the course that when we're doing dimensional analysis, meaning that we're converting a unit to a unit, if it has more than one dimension, like if it's squared or cubed or so forth, you put the cube on the outside. What that means is that in 1 cubic meter, there are 100 cubic centimeters. Not only does that cube the unit, but that also cubes the numerical value. So that's important to remember to do, because if not, then you'd be missing. You'd be 100 versus 100 cubed. So converting this, we get this value, 1.35951 times 10 to the 4th kilogram per cubic meter. And our G, and I'm sorry, I'm just such in the habit of saying G, grams, mass, that's actually gravity. So we're on the Earth, so our gravity pushing down on us is a constant. That's 9.8 meters per second squared. We could calculate these same pressures in space or on a different planet if we're given a different constant for gravity. But here, this is from physics, 9.8, and then this is written out even further, 9.80665. So this gives us all the values. You can see we have meters, kilograms, meters cubed, meters, and seconds squared. All of those units will be able to work well together so that we can get our pressure units. So let's see how this works. So for our pressure, we're going to take our height, we're going to multiply by the density, and we're also going to multiply by gravity. We get 9.33, 10 to the 4th, kilograms per meters, seconds squared. Kilograms is in the numerator, meters and seconds squared is in the denominator. All of these units together, this specific ratio with the kilograms, the meters, and the seconds squared is what's equivalent to what's been defined as a PA, which is the abbreviation for a Pascal. So this gives us pascals, and then we can branch off from that pressure unit. We'd need to look up or be given the other equalities. So there's an equality for atmospheres to pascals, and it's 101,325 pascals in 1 atmosphere. We do the dimensional analysis here and cancel out pascals. We're left with 0.921 atmospheres. We could do the same thing with bars. We can convert from atmospheres to bars or from pascals to bars, depending on the equality that we're given. In this one, it's not written down anywhere other than just in the solution, but you could find this in the table. And there are 1.01325 bars in 1 atmosphere. We cancel out our atmospheres, that leaves us with bars. So a really important thing to remember is to make sure our units cancel properly. The second part here with the solution is the easier part because we've already converted the units into what they need to be in. So hopefully you'll remember now as you watch this video that for pascals we need the units of kilograms per meter second squared. So we need all of our individual variables to have kilograms, meters, and seconds squared in their units, or they won't cancel out to properly give Pascal. We can avoid these errors by becoming familiar with the value of atmospheric pressure in various units. A column of mercury slightly less than 760 millimeters is equivalent to slightly less than 101,325 pascals, which is slightly less than 1 atmosphere and slightly less than 1 bar. These are some equivalent values. At sea level, pressure is 1 atmosphere. It's also equal to 760 millimeters mercury, and also equal to 101,325 pascals, 101.325 kilopascals, and 1 bar. Bar in atmospheres are 1 to 1. So let's take a look at 11.3. So 11.2, excuse me, I got a little bit of allergies from pollen bugging me. In 11.2, it was getting us to think about pressure units. Now that we have an idea of that, we can actually apply this to pressure and volume calculations. Ultimately, these calculations are going to be able to relate pressure, volume, temperature, and amount, the amount being in the chemical counting unit of moles. So let's read through this one. If you're peeking down at the bottom, you can see that it's relating pressure and volume. If a skin diver takes a breath at the surface, filling his lungs with 5.82 liters of air, what volume will the air in his lungs occupy when he dives to a depth where the pressure is 1.92 atmospheres? And it tells us to assume constant temperature and that the pressure at the surface is exactly 1 atmospheres. So this is one of our gas laws. It's relating pressure to volume. 1 represents our initial state that we're looking at, and 2 represents our final state. We set it up like this, and what we find from our law is that pressure and volume are inversely proportional. If we increase pressure, then we decrease volume. If we decrease pressure, then we increase volume. So one does the opposite of the other. We can rearrange this to solve for V2. The reason why we're solving for V2 is we know the initial pressure and volume, and we also know the final pressure, but we don't know the final volume. It's not a bad idea to the side to write P1, V1, P2, V2, just in a little small table or just written off to the side as a note, and label what's what. So this would be our initial volume, so you'd write that for V1. And the surface, the key thing is that it's 1 atmosphere at the surface. So that would be one that you think you might be missing. 1.92 would be our final pressure. So we can solve this for V2 by dividing both sides by P2. We get this relationship. Plugging in all of our values, we have 1 atmosphere, we have liters, and we have atmospheres. Atmospheres cancel. We don't have to do anything with units, being that we don't have to do any dimensional analysis to change units. We're left with liters. And then this is 3.03 liters. The thing to think about is to remember that pressure and volume are inversely proportional. If you increase one, you decrease the other. So at a higher pressure, the volume should be smaller. And this volume, 3.03, is smaller than the initial. So that makes sense. All right, let's look at 11.4. This reads, a sample of argon gas that originally occupied 14.6 liters at about room temperature, which is 25 degrees Celsius, was heated to 50 degrees Celsius at constant pressure. What is its new volume? So now we're looking at another gas law that relates volume and temperature. These are directly proportional, unlike pressure and volume. Directly proportional means that if you increase one, you also increase the other. If you decrease one, then you decrease the other. So they copy each other. Pressure and volume do the opposite. Volume and temperature, however, do the same thing. A key thing here is that we do need to convert our units. For gas equations, units are usually not in Celsius, they're in Kelvin. So we need our conversion of adding 273.15 to a temperature that's in degrees Celsius so that it is in Kelvin. They've already done that for us. So the room temperature is now 298.15. The warmer temperature is 323.15. And then here's our volume. That doesn't need to be changed. Again, to the side, write down what the initial and final is, or the 1 and 2. You can write 1 and 2, or you can write I and F, whichever you're more comfortable with. It's the same thing. So rearrange this to solve for what's not known, and it says what is the new volume. So it already tells us. So we can say what is the new volume, that must be the V2. We can solve for V2. So ways we can do that, we can multiply both sides by T2. That should isolate V2. So V2 is V1 times T2 all over T1. Putting in our units and numbers, 14.6 liters. Here's our temperature, our T2, and the T1 temperature. Doing the math, canceling out Kelvin, we're left with units of liters, and this is 15.8 liters. We can see that the temperature increases, and that causes the volume to increase. So that makes sense, because those are directly proportional. So big picture here is to make sure you know how the units affect each other, or how the variables affect each other. What does pressure do to the other components? What does volume do? What does temperature do? If you increase pressure, how does it affect the other components when different ones are constant? So continue on here. We're going to do 11.5. If we combine 3 liters of nitrogen monoxide and 1.5 liters of molecular oxygen, and they react according to the balanced equation, and this is balanced for us, stating that 2 moles of nitrogen monoxide gas and 1 mole of molecular oxygen gas react to form 2 moles of nitrogen dioxide gas. What volume of nitrogen dioxide will be produced? So this is applying stoichiometry concepts into gas laws as well. One thing that it does tell us is that assume that the reactants and products are all at the same temperature and pressure. So we have temperature and pressure constant. What that's going to allow for is moles and volume to be calculated. We're going to use another one of our gas laws. All of these are outlined in the PowerPoint slides in the text, so you should be familiar with them. Our solution. Volume is proportional to number of moles, and our balanced equation will allow us to give our ratio of reactants to products. The amounts of the reactants are given from the coefficients in our balanced equation. So according to the balanced equation, the volume of nitrogen dioxide formed, which is, we have 2 moles, will be equal to the volume of nitrogen monoxide that reacts, which is 2 moles. Therefore, 3 liters of nitrogen dioxide will form. So this one didn't even work it out. This is really taking into account your understanding of what happens with units. If you did want to prove it to yourself, you could set it up just like this, where we're going to have our 2 volumes. So we would have V1 over, instead of T, you'll use a lowercase n to represent moles. So V1 over N1 equals V2 over N2. And you should be able to solve that. When temperature increases at constant pressure, the volume of the sample increases. When the volume of the sample increases and the temperature is constant, then that means that there must be something else happening, and there must be more material being added, more material formed. So that would be number of moles. Right, so let's start to combine these gas laws together. And we'll take a look at this through example in 11.6. So I know you've probably already looked at the background slides. If you haven't, go ahead and look at all the background slides, look through the text, make sure you're comfortable with, at least know the name of the gas law, what it means, how the functions affect each other, the variables affect each other, being pressure, volume, temperature, and moles. And then come back and take a look at these problems we've been working through. This reads, if a child releases a 6.25 liter helium balloon in the parking lot of an amusement park where the temperature is 28.5 degrees Celsius and the air pressure is 757.2 millimeters mercury, what will the volume of the balloon be when it has risen to an altitude where the temperature is negative 34.35 degrees Celsius and the air pressure is 366.4? So we want to look at our units that we have in this problem. We have volume, we have temperature, and we have pressure. So since we have three things changing, that means that those are not, like volume's not constant because it changes, temperature's not constant because it changes, pressure's not constant because it changes. So we're going to use the formula that has pressure, volume, and temperature, which is like a combined gas law problem. One thing that's not here that's listed is moles, which is N. So what that means is the amount of it is constant. So the amount in moles is constant. And that makes sense because the helium balloon was filled and probably tied off, and none of it was released or added to the balloon. So we know that we can assume that there's not a hole in it and it's releasing material. So just that size of the balloon changes as it is in a different environment as it goes up in the air. Alright, so our strategy here, there's a fixed amount of gas in moles, as I mentioned. We're going to use this P1V1 over T1 equals P2V2 over T2. Essentially what they've done is they've combined the pressure volume formula with the volume temperature formula and just pushed them together. We can see that pressure and volume, because they are both in the numerator in the initial and the final state, they're inversely proportional, meaning that if you increase one, you decrease the other. If they are one over the other, then that means they copy each other. So pressure and temperature, if one increases, the other increases. If volume increases, then temperature increases, and so forth. If you want to convince yourself that, you can just put in some numbers here, like 1s and 2s and 3s and so forth, and do the same thing over here, and solve for one, and kind of see what happens when you increase and decrease each one, and convince yourself, if you need to. But anyways, to not get off track, let's go back to this problem. The only value we don't know is V2. Temperatures must be expressed in kelvins. We can use any units of pressure as long as they're consistent. So our solution here, what we don't know is the final volume. Everything else is given. We have P1 T2 V1 over P2 T1. So what has been performed so far is some algebra to isolate V2. So they needed to multiply both sides by T2, that cancels it out on this side. Also needed to divide by P2. And then this just arranges everything, numerator and denominator, all together. Then we can plug in all of our values. So the hard part might be actually rearranging this using algebra, so practice that if you need to. So plugging in our initial pressure, we have 757.2 millimeters mercury. The temperature in Kelvin is 238.8, and that's the final temperature. Our volume initially is 6.25 liters. The final pressure is 366.4 millimeters mercury, and our initial temperature is 301.65. Put this in your calculator, probably do it a couple times since there's multiple numerical values, and it comes out to 10.2 liters. If we think about this, the solution is essentially multiplying the original volume by the ratio of the initial and final pressure, as well as the ratio of the initial and final temperature. The effective decrease in the pressure will increase the volume. The effective decrease in the temperature is to decrease the volume. So we got to see how much does one increase versus the other, and so forth. So the effective decrease in the temperature, or it says in this case the effective decrease in pressure, predominates and the balloon volume increases significantly. So there could be some problems that are a little bit tricky in that you may have an increase in pressure and a decrease in temperature, and you may have it work where the volume doesn't change because the pressure increase and the temperature decrease offset. But as it stated in this case, that pressure change was so much of an influence that it really changed that volume. So just trying to elaborate to have you think about these things. All right, so now let's incorporate everything. Let's look at pressure, temperature, volume, and moles. Now, we can do this without using, well, there's two ways that we can do it. You can look at an initial and a final state, where you use ones and twos. Or you can look at just a situation, just one point. Not an initial and a final, but just one point. So if you're just looking at one situation, then you can use this formula here that I'm leading to, which is the ideal gas law. If you're actually looking at the change, then you need to have two things equal to each other with the ones and two. The ideal gas law so that it can work. So if we're just using one state and we need units to cancel, there needs to be one more thing in there. That one more thing is this uppercase R, which is a gas constant. This will allow units to cancel so that you can take one state, meaning that you don't have changes in pressure, temperature, and so forth. We're just looking at one moment. And then this gas constant, which it's constant so it remains the same, is going to have units so that the other ones will play well. Play well meaning that they will cancel out so that you're left with one unit if you isolate it. So hopefully that makes sense. Let's take a look at it and see how the units will cancel. So we're going to calculate the volume of a mole of ideal gas at room temperature in 1 atmosphere. The strategy here is to convert the temperature of Celsius to kelvins and use the ideal gas equation to solve for the unknown volume. The data given is 1 mole for N. Our temperature is room temperature. In Kelvin is 298.15. And pressure is 1 atmosphere. We want a gas constant, and there's more than one gas constant. The gas constant you want is the one that will actually cancel out the units that you're given. In this case, we want one that has liters, atmospheres, Kelvin, and moles. This one has a number of 0.08206, and then here's the liters, or the units. Liters and atmospheres in the numerator, Kelvin and moles in the denominator. Our ideal gas law equation, which isn't written, is PV equals nRT. So it's pressure and volume equal to moles, gas constant, temperature. If we're looking for volume, we can divide both sides by pressure and we get this relationship. Excuse me. Putting in the numbers for the variables, N is 1, R is our gas constant, here's our temperature, and here's our pressure. We can double check and always double check to make sure you use the right gas constant. Moles isn't in there, so it remains. Atmospheres over atmospheres is 1, so that'll cancel. The Kelvin will also cancel. And I'm sorry, there's moles. Moles does cancel too. Good, so we're left with one unit, which is liters. Performing the math here, 1 times this value divided by 1, we get 24.5. This is also a constant that you can remember. So at room temperature, they're in 1 mole, doesn't matter what it is. So 1 mole at room temperature and normal sea level pressure is going to take up a volume of 24.5 liters. And this is a constant, so this is a good one to remember. So with the pressure held constant, we should expect the volume to increase with increased temperature. Room temperature is higher than the standard temperature for gases, which is 0. So the molar volume at room temperature should be higher than the molar volume at 0 degrees, and it is. Let's go ahead and stop here. It's about 30 minutes. I will go ahead and make a part 2 to this video and wrap up the remaining examples. Thanks.